Hey, this is lab4 oscillations. The purpose of this lab is to observe the movement of a mass on a spring, and by doing this we'll be able to identify forces and energies at play. We'll also create a computer model of this motion, and this will allow us to see how accurate our predictions were. And it turns out that the predictions were pretty accurate, although they were somewhat faulty. And we'll see that coming up. Principles at work are Newton's second law and energy principle, which this is what we're working with right here. The tracker video that we analyzed, there were two important things that were obtained from it, the oscillation length and the position values, and these will come back up later. And also video frame length, calibration length, and relevant masses are the same from the tutorial video on Coursera. So here's the running of the model. The blue dot is the model, and the red dot is the motion of the ball that we analyzed. It's a little bit off, but that can be due to the time step, since the picture frame of the video was a lot less, or a lot slower than the time step of the physics. And we'll come back to this graph in just a little bit. The coding is right here. So the initial conditions were set, the ball's position as well as velocity, and it started from at rest, so the velocity was 0. And over here, all the other important things were set, allowing us to incorporate spring force and gravity force. And here's some more code that was used. The important things to gather from this are the usage of forces, velocity and position, which is Newton's second law, which is right here, as well as the energy principle, which is right down here. And also this was the calculation of the graph, which will be discussed very briefly. So the spring constant was determined by using the spring force equation and motion principles in order to come up with this equation. And T is the oscillation period, and since we have the oscillation period as well as mass, we can calculate the spring constant. And so the oscillation period is calculated by taking the difference in time between where the mass returned to its original position. And so I determined that spring constant equaled this figure right here, 5.86. Using this, I also calculated spring length using also the spring force equation. And I determined spring length to be equal to 0.028 meters, although this is where my error came in, because that resulted in a very short spring and not a lot of movement. So I think that there was some discrepancy, which I will talk about very briefly, very shortly. So what does it all mean? The energy principle, since our system for energy was the earth and the mass and the spring, and the only forces acting the only energies that were kinetic energy, potential gravitational energy, and potential spring energy. That means that overall change in energy will equal 0. And this was apparent in the graph that was plotted by the model. This red line is the potential spring energy, green line is the potential gravitational energy, and blue line is the kinetic energy. And this yellow line through the x-axis that you can't see very well, but it's right on the x-axis, is the overall energy, and that stays at 0 the whole time, which or that's the overall change in energy. So that's good, because that's since energy was preserved, and that follows by the law of conservation of energy. The oscillation periods, so I use the x values to calculate my t equals 1.65, although I could have also used the y values to calculate where the mass returned to its original position. And I think that this little discrepancy of 0.13 may have affected the error that I discussed with the spring constant. So that was it's important to note errors like that. So in conclusion, you must consider the system in order to determine change in energy, and the law of conservation, as we see through this project, does hold true. So also it's important to be able to use a scientific method in order to detect errors such as my spring length error. Thank you.